Today we want to combine chapter 6 and chapter 5 so that we can solve some strange stuff. So here's an equation. Let's solve 3 cosine squared theta plus sine theta is equal to 3. Let's limit our theta to be between 0 and 360. Let's go for theta between 0 and 360 degrees. All right. So this is what I would call a strange equation. Note that we can't do inverse operations in reverse order because the variable appears more than once and it appears in multiple contexts. It's part of a sine and it's part of a cosine. So we're going to have to do some algebra stuff on this equation. And in trigonometry, some algebra stuff means some trig identity stuff. So the first thing to note, can't do inverse operations in reverse order. The variable appears more than once. We can't just do inverse operations in the reverse order. The variable appears more than once. And moreover, we can't combine the cosine squared theta and the sine squared theta into just one expression. Bummer. So we've also got this cosine squared and a sine. So we can't do that thing that we did before where we just make a substitution where delta is equal to sine of theta. So what we're going to have to do is combine the, replace that cosine squared with the sine squared identity. I want to somehow get either sine to be a cosine or cosine squared to be a sine. We want to try to get this down to one trig function. So our first strategy is we got cosines and we got sines. We want to try to get down to one trig function. That is just sine or just cosine. There's more that goes into this than trying to get just sine or just cosine. Referring to our previous conversation, I know what to do, so that's what I'm going to do. But how do I know what I'm going to do? The answer is, been doing trig for a very, very long time. That's all it is. It's just a factor of it's just a function of time. But the other reason that I'm thinking this way is that I can't separate by factors. One of the things that we have that's very powerful is that if we can look at a product and write a product that's equal to 0, then one of the other factors has to equal 0. It essentially splits the equation. So notice, so we don't have factor times factor equals 0. We don't have factor times factor equals 0, or factor 1 and factor 2. We don't have a product that's equal to 0. That's one of our strategies, is to get a product equal to 0, so then I can split the equation. So that's a very powerful maneuver, but it requires a very specific thing, a product that's equal to 0. If a product is equal to 0, then one of the factors must be 0. Don't have that. We don't have a product. We don't have a 0. Total mess. So what we're going to do is replace the cosine squared with an identity, because I know I can turn a cosine squared into a sine squared. So I'm going to say cosine squared theta is 1 minus sine squared theta. And this will get all my trig functions to be one trig function. So my equation looks like 3 times 1 minus sine squared plus sine theta is equal to 3. We're better off here because we only have one trig function, sine of theta. There's an instance of the sine theta being squared, but that's okay because then I'll have a sine squared theta and a sine theta. Maybe it's quadratic in theta. Let's see what happens when we simplify some stuff. So if I simplify, I get 3 minus 3 sine squared theta plus sine theta is equal to 3. Well, lucky us, the 3's cancel out, and we get an even easier quadratic in sine of theta. So let me simplify this. I'm going to cancel out the 3, subtract 3 from both sides, and I don't like my leading coefficients to be negative. So I'm going to move everything over onto the other side and then flip the sides. Or you can multiply by -1. Those two 3's drop out. Now I can rewrite this equation as quadratic in sine. Did that a lot last week. Now we can make a substitution, and I can trade my sine theta for just a w. Then the equation looks like 3 times w squared minus w equals 0. And so now we're looking at quadratic in sine theta. It's also easy to factor. I'll have w times 3w minus 1 equals 0. So w equals 0, or w equals 1/3. But we're not here to solve for w, we're here to solve for theta. So since w is equal to sine of theta, instead of w equals 0, I can go back over here onto the theta side, and I'll say that sine of theta is equal to 0, or sine of theta is equal to 1/3. Here's where we use that 0 property to split the equation into two equations. So for the sine of theta is equal to 0 part, this is just a memory check. If we think about the graph of sine of theta, this tells us that theta is equal to 0, or theta is equal to pi. Oops, sorry, or 180. Forgot that this problem's in degrees. Then we have to make sure that we have to add integer multiples of the period. So plus 360 degrees times n plus 360 degrees times getting a delivery, I think. So where were we? Ah, yes, we're getting all the solutions for sine of theta is equal to 0. So we get 0 plus multiples of 360, and we get the 180 plus multiples of 360. Now we can summarize this. We can take both of these and just say we're getting all the multiples of 180. Because we get 0, then plus 2 pi, 0, 360, 720, and so on. But we also get the 180. 360 is just two 180s, but we also get the 180 after that. So 180 plus 360, 540. Yeah, I'm not going to be able to do arithmetic. So we can summarize these two solutions with 180 times n. Or I can go back and remember that I said solve for theta between 0 and 360 and just say, and not worry about that. And just say theta is equal to 0 degrees and 180 degrees. So that's the first part of my solution from sine of theta is equal to 0.
Why don't you include the 360 degrees? Is it less than 360 or is 360 not included?
Yeah, because I just said solve for theta between 0 and 360 at the beginning. So I didn't have to worry about all the multiples of 360. So 0 plus 360. Oh, I suppose I did include the 360 in my original. I see what your question is now. So the other part of the equation where sine of theta is equal to 1/3, that's not one that we recognize. So we'll just have to go to the calculator. Our problem is in degrees, so I'll switch my mode to degrees. It already was. And we'll do a sine inverse of 1/3. This will give us a reference angle of 19.5 degrees. So our reference angle is going to be the sine inverse of 1/3 or 19.5 degrees. The sine of the angle is positive, so we have to look at the angle, the quadrants where sine is positive, and that's quadrant 1 and quadrant 2. Sine is positive in quadrant 1 and quadrant 2. So I'm going to put a 19.5 degree reference angle in quadrant 1. And I'm going to have to put a 19.5 degree reference angle in quadrant 2. So that'll be 180 minus the 19.5. So 160.5. I'm going to remember that I restricted the solutions to between 0 and 360. So here are my two more answers, 19.5 and 160.5. So this is an extension of a problem we did last week, but where we have a trigonometric equation that's quadratic in sine or cosine, and that we had to put in to one trig function using the Pythagorean identity. And it also combines solving a trigonometric equation where we had to use a machine to get the reference angle, but the process is still the same. Once we get the reference angle, put the reference angle in the appropriate quadrants, and then add multiples of the period if it's called for. Any questions? So at this point, we're solving kind of strange equations. And they're very niche equations. But that's good training because it involves remembering all of these things. We have to remember how to solve quadratic equations. We have to be able to see quadratic equations in different contexts. We have to be able to, we have to train our eyes to look for quadratic equations where it's not just ax squared plus bx plus c equals 0. We have to find a times sine squared theta plus b times sine theta plus c equals 0. Any questions? Here's another cool equation that involves a similar strategy. So let's suppose we wanted to solve sine x plus cosecant x is equal to 2. Here I didn't restrict the x, so we're going to solve for all x. The question is always where to begin. What do we know? What can we do? One thing that we know is that sine and cosecant are related. That's why I picked sine and cosecant. Sine and cosecant are related, and they're related with a reciprocal identity. So I'm just going to replace cosecant with 1 over sine x. So I'm going to say sine x plus cosecant, which is just 1 over sine x. So we're just going to use a reciprocal identity. Now we have to look at this equation, and we got sine x plus 1 over sine x. And we have to think about what's the defining characteristic of this equation, because that's how we train ourselves to solve equations. We look for what's going on. I'd like to do inverse operations in reverse order, but the variable appears more than once, so not going to work. The main thing that we notice here is that a variable, and one instance of the variable appears in the denominator. We notice that everything is in terms of sine, but one of the instances of the variable is sitting in the denominator. The sine x is in the denominator. So by replacing cosecant with 1 over sine, I've put a variable in the denominator, and that's given me something to do. So now there's a variable in the denominator. So now we're pretty happy. We've got a variable in the denominator, which gives us something to do. I can solve like a rational equation. So I can make a substitution like I did before, where w is equal to sine of x. Then my equation looks like w plus 1 over w is equal to 2. And our strategy for solving rational equations is to multiply by the common denominator. So to solve a rational equation, we multiply everything by the denominator. So then it becomes w squared plus w is equal to, I was thinking of the other term already. I don't know if that's a too much coffee problem or a not enough coffee problem. So with w squared plus 1 equals 2w. Which is quadratic in w. It's like I planned this to be quadratic in w again. So boring. All my equations are the same. So with w squared minus 2w plus 1 equals 0, we can factor that. And so w is equal to 1 and it has multiplicity 2. So w equals 1 twice. We can take that back over to the sine side of things and just solve the equation sine of x equals 1. So if we think about the graph of sine of x is equal to 1 at pi over 2. That's the only time sine of x is equal to 1. And then we'll add multiples of the period. So once we find out that sine of x has to equal 1, then it just becomes a memory check. You got to remember what our graph of sine looks like. Or we could think in terms of the unit circle. Well, this goes on forever. Or we could think in terms of the unit circle. Sine is the y coordinate. So that only happens that one time at 0, 1. And that happens at pi over 2. So by using that reciprocal identity at the beginning, that put a variable in the denominator. And the important part there is that it gave us something to do. Now that there's a variable in the denominator, we can multiply through by the common denominator to clear it out. And then that sets us on the path. Now, I wrote the problem with a substitution. I replaced my sine of x with a w, which is why I like to have one trig function if I can get it. But there's no reason that you had to do the problem that way. So you could take this equation. I'm going to smear all this, yikes, or write weird. I could have taken sine x plus 1 over sine x is equal to 2 and multiplied all that by sine x. So if you find an explanation of this problem, we'll probably ignore the fact that this is relying on our strategies for solving rational equations, solving an equation where the variable appears in the denominator. The strategy for solving an equation where the variable appears in the denominator, one strategy that is to multiply by the common denominator to get a polynomial equation. And so all the same stuff happens. This becomes sine times sine, or sine squared x. 1 over sine times sine is 1. And over here we get 2 sine x. And we're at these two line up. And then I would rewrite that at quadratic style. Sine squared x minus 2 sine x plus 1 equals 0. And then I can factor. So you don't have to convert the problem into W. It's just easier to see. And the reason I like to convert things over, to substitute over into W, is that it makes it look like something that's more familiar. It makes it look like the rational equation, because that's the strategy that's in play. Any questions?
I just have a quick question because I might just be losing my mind. So if you go back up there where you have that sine x plus 1 over sine x equals 2, if you just multiply sine x by sine x over sine x, so you're multiplying it by 1, you get sine x squared over sine x plus 1 over sine x, and then they've got the same denominator, so you can combine that into sine squared x plus 1 over sine x. Is that right?
That is correct.
Does that get you anything? That sine squared, I don't see an identity with the sine squared x plus 1, but is there something out there?
So you're employing the strategy of get a common denominator on these first two terms. So the answer is yes. Sine x, if we want to add 1 over sine x, if you get a common denominator, if you by multiplying this first term by sine x, this is also good instinct. This is perfectly correct instinct. So look at the sine x as being over 1 and think get a common denominator. That gives us sine squared x over sine x plus 1 over sine x. And now that we have a common denominator, we can combine the numerators. So it's going to be sine squared x plus 1 over sine x. This is still all equal to 2.
Good question. Couldn't you have just canceled out the sine x in the beginning?
Cancel out where?
Oh, at the beginning, because it's sine x over sine
Here?
of x. Yeah, right there.
Well, we put this here so we could get a common denominator. If we cancel it out, we're back to where we started.
Oh, okay, that's right.
So here we're doing the strategy of get a common denominator. So this is still equal to 2. If I multiply both sides of the equation by sine x, if I multiply the equation now by sine x, the sine x cancels on the fraction side, and I end up with sine squared x plus 1, and it appears on the other side, 2 times sine x, which is the same situation we were in before.
Okay, right, got it. Thank you.
The best thing to do is whatever it occurs to you to do first. Some people look at the equation and said, it's a rational equation. I'll multiply by the common denominator all the way through. Someone will see I have fractions that I can add. I'm going to add those fractions. It still ends up being a rational equation. So you multiply by the common denominator and get a polynomial equation. Any questions? Now, keep in mind, you don't get to look at these equations and say, man, how am I going to learn how to do these equations on the final? Because the final is exclusively these equations, and I want everybody to flunk. Wait, no, that's not it at all. These are weird equations because it relies more on our algebra and our memory for trig identities than to actually have practical equations that we'll need to solve. For the most part, the exercises that we do in any math class, really, they're not representative of things that you're actually going to do in some job somewhere in the future. This is not practical knowledge for your job as a future fill in the blank. I can't teach that class. It is just straight up impossible for me to train you for your future job as a fill in the blank, because have been explicitly banned from looking into the future and seeing what your job is so I could figure out what to teach you. They're like, oh, Leach, you can't be telling people what's going to happen in the future. I'm like, oh, but it's so helpful. And they're like, oh, dude, you've seen that movie. You know it ruins your life when you know what's going to happen in the future. I'm like, oh, you know what? You are right. That whole butterfly effect thing. You know what I mean? So I'm not allowed. I can pretty much promise you that whatever your job is, unless it is math teacher, specifically trigonometry teacher, you'll probably never have to solve a trigonometric equation after this class ever in your life. In fact, if you have evidence, if you can get video evidence of a trigonometric equation that you have to solve for your job, and you are not a math teacher, then send me video evidence and I'll send you $20. But it's got to be convincing evidence that you had to solve this equation, trigonometric equation, or you're going to get fired. And you had to do it. You know what I mean? But the offer is not valid for people that become teachers because you're going to be solving lots of trigonometric equations. But remember, solving the equations isn't really the point of the work. Just like when you go to the gym and start doing lateral raises, that is not how you pick stuff up. Lateral raises is not how you should ever be picking stuff up. But it's still useful. It still trains, it goes after a particular muscle group that is used to support other muscle groups doing actual things that we ask the human body to do. You know what I mean? There's the exercise where, I can't remember what it's called because I don't go to the gym, which is super obvious, but I don't go to the gym, where you're trying to strengthen your back and you're using your back to lift something up heavy. And that's something that you should never do. You don't lift with your back, you should lift with your legs. Unless I guess you're in the gym and you're trying to strengthen your back. But the point is not that you're preparing to lift things with your back in the future, because that's just a recipe for getting hurt. The point is strengthening your back so that you're better at lifting things the proper way. You know what I mean? Plus, it's fun. We do it because it's fun. There's one more equation that I want to look at that also has a useful bit of information. So let's suppose we wanted to solve sine of 2x equals sine of x. The amount that I write in the problem just decreases as we go. In the beginning, it's solve this equation for this range of theta. Next one is just solve this equation. Forget the theta part, forget the range part. And now I'm not even saying solve, I'm just dropping an equation in front of you because it's an equation. And the only question that'll go with it is solve. So once again, this is going to rely on us not necessarily knowing what to do, but looking at what we have and thinking about what we can do. And what we can do is that sine of 2x, replace that with a double angle identity. So sine of 2x is 2 sine x cosine x. And this is equal to sine x. Now, at this point, we come to the point of this problem. Right now, we see a factor of sine x on the left, and we see a factor of sine x on the right, and we're going to be super tempted to divide by sine of x. Because if 5x equals 10, we divide both sides by 5. The problem is we can't just go around dividing by sine of x. Why can't we just divide by sine of x?
Is it because you don't know what quadrant it's in?
It's different than that. It's actually more of an in-between quadrants thing. We don't just want to divide by sine of x. Why can't we divide in this case?
Oh, sine x might be undefined.
Sine x might be 0, and so dividing by sine x might be undefined. We know that there are certain values of x for which sine of x is equal to 0. And so if we go around dividing by sine x, we might be dividing by 0. And if we start dividing by 0, the math cops come down, break through your door, and you get arrested and you go to math jail. I mean, notice there are only 18 people here today. There's like 40 people. Most of them got arrested and thrown into math jail. Don't mess around. Math cops play hardball. So don't just divide by sine x, because sine x might be 0. Not all the time, but it might be. And so dividing by sine x might be divided by 0. Dangerous thing. But what we can do is notice that, so we have this mixture of sines and cosines. The only way to mix this into one trig function is the original equation, but then we have the 2x and the x, and that's not good either. What we can do is put everything on one side. Here's how we deal with things that we want to divide by but can't divide by. Get everything on one side, and that thing that you want to divide by but you can't divide by because it might be 0, put it on the other side, factor it out. This is how you, in an equation, you deal with things that you want to divide that you can't divide because they might be 0. It's terrible when you say it in words. This is how you deal with things you want to divide but can't because they might be 0. You put it on the other side of the equation, you factor it out. And you say, what happens if that thing is equal to 0? Because now we have a product that equals 0. So I got to solve sine x equals 0 and 2 cosine x minus 1 equals 0. If there's a factor that's never going to be 0, you can go ahead and divide by that. But if there's a factor that might be 0 and you want to divide it out, what you do instead is to get everything on one side of the equation and factor it out. You might have been told in your solving equations history that when you divide by sine of x, you also have to solve sine x equals 0. This is why. because you were given a shortcut. And you got to worry about times when you divide it by 0. So better to subtract and then factor that thing out. So for sine of 0, we get x is equal to 0 and pi. I guess if we keep going around the circle, we also get 2 pi and 3 pi and so on. So we could summarize this by saying x is equal to pi times n for any integer n. For the other half of the equation, once we use the 0 property to split the equation into 2 equations, I have 2 cosine x minus 1 equals 0. So cosine x is equal to a half. Now we need a reference angle. It's pi over, so cosine of sine of 30 is a half, so sine of 60 is a cosine of 60 is a half, so it's pi over 3. And we need to put that in the quadrants where cosine is positive. So that's in quadrant 1 and quadrant 4. So our pi over 3 in quadrant 1 is going to be pi over 3, and then we'll add multiples of the period plus 2 pi times n. Or in quadrant 4, we can write x as 5 pi over 3 plus 2 pi n. So here are our infinitely many solutions. Oh, make sure to fill this in so they don't leak out.
When will the final be? Like not final, but when's the next assignment? I mean,
Not sure. Everything will be done by December 9th.
oh,
That's the
okay.
last day of class. Any questions? All right, so today was about combining trig identities with solving trig equations. The core mechanic of solving equations we should think of that as inverse operations in reverse order. But we can't do that when we have the variable appear more than once, or the variable appears, well, if the variable appears more than once. Then we have to just learn different reactions to the variable appearing more than once. A lot of algebraic solutions mean trying to get to a polynomial equation that you can factor. Or just get to a quadratic equation, a polynomial equation, because a polynomial will always be a bunch of linear factors and quadratic factors. And everything else is just strategies to get to that point. When the variable appears in the denominator in a rational equation, we multiply by the LCD to get to a polynomial equation. If the variable appears under a radical, then we square both sides to get a polynomial equation. And then we just have to know all the extra things that go along with those processes. But you got to keep in mind that the reason that we're doing these weird reactions is that we can't just do inverse operations in reverse order like we want. This is despite the fact that we always teach math from the standpoint of functions, and that then here we go do all these weird things where we're not solving with inverse functions. It's weird. All right. All right. So that's going to do it for today. I will see you all on Thursday. Everybody have a good couple of days, and thanks for playing.